much. Great to be here at CERAWeek. Thanks everyone for being with us for this session. So Blykalla is a Swedish company developing advanced small modular reactors. We are developing a product called the Sealer, the Swedish Advanced Lead Reactor. It's a 140 megawatt thermal, 55 megawatt electric output reactor in an extremely compact format. It's about 6 by 6 meters or 20 by 20 feet, which means that it can be serially produced in a central location and shipped to site. So if you think about it in contrast to how conventional nuclear is built, you can think of us as more of like the Vestas, to take a page from renewables, or the Siemens Energy of nuclear. The idea is that these units can be assembled with a workforce that does that over and over again. You take out a lot of the project risk from a large site-specific construction project, and you can achieve both learning curves, but also predictability on the cost. Actually, our primary system is about the same size as the Siemens Energy gas turbine, which is exactly what you have packed up on the picture here, leaving the assembly workshop in central Sweden to be shipped to site. Let me talk a little bit about lead cooling and why this is key to our technology. So I want to position this in the spectrum of different nuclear designs that are being pursued right now. The majority of commercial nuclear is based on using water as a coolant. This is what the world settled on 40, 50 years ago, and I've been building out. And nowadays, we're also building or developing SMRs based on light water technology. But I think SMRs have become a very wide tent with a lot of different types of technologies and reactors under that tent. So what we display here with the numbers is the height of the system. And you can see some of the light water designs, 25 meter high construction units. Those that are developing those reactors often market them as a version of already built and proven large scale reactors, which I guess is attractive to regulators. But you're still talking about large construction sites. The Swedish state-owned utility Vattenfall, choosing between the two vendors listed here for their site in southern Sweden, they estimate that 3,000 people will have to work on the site for closer to a decade. So, you could argue how small or how modular it's really become. So I think this is really the problem statement that has given rise to the focus on all these advanced designs that you see here. And without going through all of them, in a nutshell, lead offers the possibility to have a very strong, inherently passive, safe reactor in a very compact format. So you can see the relative size here of the units. If you take the properties of this compact lead-cooled reactor then and turn it into sort of a value proposition or the competitive advantages for a customer buying these units, it comes down to three things. And I mean, these three things probably match pretty well to anyone who's a bit skeptical on nuclear. If you ask someone on the street, what are their concerns, they'd probably talk about, hey, it's expensive, takes a long time, what about safety, and are we leaving a burden for future generations? And I want to argue that with this technology, we make a step change improvement across all of these dimensions. So thanks to the compact size and this serial production and central assembly, we're able to put them together in 20 weeks. We're able to take a site from order to commission in 2 years once we're up and running in serial production. And I think in no other business is the saying that time is money more true than in nuclear. If you have large capital costs that you need to finance with interest and revenues that are discounted far out in time, that hits your LCOE calculation. And this is a big part of why you can get a much more competitive lifetime cost with these units. On the safety concept, I think it's important to note that all nuclear is of course safe. It's about how you achieve the safety and what precautions you need to take and what limitation that imposes on you. With our safety concept, we believe that you can have extremely small planning zones around the reactor, and that this enables co-location and very flexible siting, where historically you haven't been able to deploy nuclear technology. And then lastly, our technology is what's called a fast breeder reactor. means that you don't have any fuel change over 20 years of the fuel residency. It actually breeds more fissile material while you run it, so it becomes very economical to reprocess the fuel at the end of that 20-year fuel cycle. If you go into a closed fuel cycle, you extract more than 100 times more energy from the uranium ore. You leave a fraction of the waste. The waste you do leave behind is only radioactive for a few hundreds of years, as opposed to 100,000 years for the spent fuel that we're planning to deposit in, for example, the geological repositories in Sweden and in Finland right now. So it's a step change on that dimension as well. Let me talk a bit about how we achieve this safety concept. It's really down to the fundamental properties of lead. So given that lead in this system, you would operate at atmospheric pressure. It means that you don't have a driving force that could disperse fissile content if you had a situation where the walls of the building, the vessel, and the fuel cladding was compromised. Lead is also chemically inactive. Water, if it becomes too warm, becomes hydrogen, and which can be explosive. There are other coolants that are reactive with water or with air. Lead is very benign, so you don't have that risk. It has high buoyancy, so if you were to lose electricity to power the pumps, you actually can rely on natural circulation to remove heat from the core. It has a boiling point of 1,750 degrees Celsius, which means even if you simulate an uncontrolled reaction in the core, you never get anywhere close to melting away all the lead. You have negative reactivity feedbacks and the temperature quickly drops again. And for the nuclear accidents that we've had, it's been part of the chain of events have been a loss of coolant accident, as it's called. Lead also binds chemically with iodine, which is one of the dimensioning isotopes for the emergency planning zones. And then lastly, as I think we all know, if you go to the dentist, you get a lead apron, right, to protect from gamma radiation. Lead is the gold standard for radiation protection. So here we have 800 tons of lead encapsulating the core. So all these factors taken together basically mean that when we apply regulatory standard and international frameworks for how you need to design the perimeters around the reactors, you end up with order of magnitudes lower zones around this. And this is the key to then being able to put this close to industrial users, close to data centers. We don't need any secondary cooling with water, so you can locate it even in places where you don't have access to a lake or to the ocean. So if this is so good, and hopefully you've understood some of the advantages of lead-cooled fast reactor technology, sort of why hasn't it been done before? So the historical barrier has really been corrosion. The technology and the concepts behind the technology dates back to the Soviet military. In the 50s and 60s, the Soviet military developed the Alpha-class submarines based on lead-based coolant. So over the past 60 or so years, we have about 100 reactor years of operational experience from these systems that we've learned from. It was 11 systems, 2 on land, 9 in submarines. You might have seen this movie, The Hunt for Red October, with Sean Connery. He pilots an Alpha-class submarine. So when the Soviet fell, the West wanted to fund the Russian scientists to make sure that we had a knowledge transfer and understood this technology. And our co-founder, Janne Wallenius, who's a professor in reactor physics, was among the first scientists to go to Moscow, got Western funding to oversee 60 Russian scientists across 3 national labs, and through that research, enable the knowledge transfer to the West. He realized that if he wanted to build commercial power-producing units, we needed to have new materials, corrosion-tolerant materials. In the submarines, they had worked with coatings, but those would probably never get accepted by a Western radiation regulator as workaround solutions. So he teamed up with Peter Chakalos, to your right here, who led the material science department at the Royal Institute of Technology. And he and his team of PhDs got to work and eventually made the first breakthrough on the Feckerel steel here. Feckerel is actually a 100-plus-year-old Swedish invention. You all have Feckerel steel in your ovens or your toasters at home. And they came up with an adaptation of this steel that provides perfect corrosion resistance in liquid lead at these operating temperatures. So today, Blykalla has developed 3 families of corrosion-tolerant materials that we've patented. And we've spent the last years building out the supply chain and partners that can deliver this. We've taken the philosophy that we want to work with leading industrial partners in order to co-develop and to advance the materials, the components, and the technology that's needed. So let me share some examples. So together with Kanthal, we've melted industrial batches of 10 tons of the steels, a Swedish steel provider. From that steel, we've made different form factors. What we see here is, for example, powders that we use for powder metallurgy applications. We've then taken the materials and started using different production techniques to make components. So together with KSB, a German pump manufacturer, we've been able to use additive manufacturing to basically 3D print some of the components, including a pump impeller, which enables us to prototype much faster than with conventional casting. With other Swedish vendors and European vendors, we've also been able to use different production techniques. For example, with wires, we're welding wires onto conventional, already approved structural materials, so we don't have to requalify the structural materials for our reactor. And we've used, for example, high-speed laser cladding to apply these to these materials. So all of this is now coming together in an advanced reactor testing site that we have built together with the energy giant Uniper on their nuclear power plant site in Sweden. You can see the nuclear power plant in the background and our test site in the foreground on this picture. And here we're bringing this into actual testing. So right now we have 4 test rigs in operation where we've taken components and run liquid lead loops to provide data on that will be used for licensing, the commercial licensing of the reactor. Together with our partner ABB, we've also set up a control room on this site. And the idea here is to show how the instrumentation and control will work, how the operators of these nuclear power plants in the future will be working in the control room. So as you've heard and understood, Blykalla is a Swedish company, but we're really building this for global deployment, and we're extremely happy that we're bringing this technology to the US. So since we started our commercialization, we've grown to about 100 people. We've raised about $100 million in funding. And last year, we raised a round that was led by our US partner and advanced reactor peer, Oklo. And together with them, we're bringing this technology to the US. You could say that lead cooling, obviously, as I explained, dates back to the Soviet. We know that they're pursuing lead cooling, for example, building a reactor called Brest 300. That's a lead-cooled reactor. China's been doing research on this technology. And in the West, we've had European research for the past 3 decades, but are now in the process of also commercializing this technology as one of the advanced technologies that can be deployed. So in addition to the non-nuclear testing in Sweden, we will build our first nuclear reactor here in the US, and that will be a stepping stone to deployment both in the US and in Sweden. I'll share a little bit more about what we're doing in these 2 markets. So last week, we announced our first site in Sweden. It's a site 2 hours north of Stockholm, where the region actually has had to say no to 4,000 jobs in the past years because they cannot provide baseload power to industrials who want to either expand or establish themselves in the region of Gävle, as it's called. So this will be our first site, and then there's one more site that will be announced in the coming couple of months. And what's unique about Sweden is that, Sweden has a proud history as a nuclear country. The corporate predecessor to ABB, Asea-Atom, built 10 large-scale reactors in under a decade back in the 70s. And the current government has made it a key priority to advance new nuclear. And one of the key policies is a co-financing framework that enables you to both get 80% debt financing of the project at treasury rates. You get a 40-year contract for difference, so basically replaces the need for a corporate offtake, power purchase offtake agreement, and it provides equity risk protection for equity investor. So all of this together is meant to ensure that private capital will flow to Sweden in order to finance the first phase of nuclear build-out in the country and support these projects and these developers until costs come down with experience and learning curves and the supply chains are built up. Now, in parallel to this, or before we get to the commercial deployment in Sweden, we will build the first reactor here in the US. The US is uniquely attractive to do that, thanks to the policies put in place, and especially the DOE's authorization framework, where, for example, where some concepts were selected under the reactor pilot program that rests on this legal foundation. It really takes new technology and creates predictable licensing timelines, an iterative way of working between the regulator and developers of new technology, which we think is uniquely attractive if you're going to take technology like ours and demonstrate it and bring it forward so that you can go into commercial deployment and commercial licensing with the NRC in parallel. So we're excited to be investing in the US thanks to these policies. And I want to close off by saying I think if the US is going to build 400 gigawatts or the hundreds of gigawatts that have been mentioned in the coming years, you really need all different technologies, and you can't afford to not bet on the full spectrum of advanced technologies. So with Blykalla and with the unique features that our technology can bring, we aim to be part of delivering on that agenda and to contribute to that. The demand side is just so big right now that we need all the technologies that can be part of the solution. So we've set as an ambition to build 100 reactor parks of 6 units each. So this is some 300 megawatts per park, 30 gigawatts all in all. And hopefully this will contribute meaningfully both to the build out in the US to serve the emerging need of data centers to have co-located baseload power, as well as the industrials in Europe that need affordable baseload power to stay competitive. So thank you all for coming. If you want to connect, you have my LinkedIn details and the QR code there, but happy to also open up for questions.
All right, we'll start the question and answer session now. If you have a question, please raise your hand and we'll get it on the mic. So let's first right here.
So compared to molten salt reactors, the lead reactor is smaller. Is that because of high heat density of lead? And can you just give a brief comparison between molten salt and lead?
Yes, I mean, with some or quite a few of the molten salt concepts, the core idea is that you dissolve the fuel into the lead and you then do online recycling of the fuel and the fission products. And I think this introduces an even harder materials challenge than what we had to solve for with liquid lead. So I think that's sort of one of the fundamentals in terms of the different approaches and the challenges. Now, there are companies that are looking to do molten salt as a coolant, but solid fuel, and I think that's sort of a slightly separate story. But to your point on why we get such a compact design with lead, it's thanks to the density, it's thanks to the properties of lead that you can simplify a lot of the design. You achieve safety through passive safety through a lot of the inherent properties of lead.
All right, next question. We can take some outside if you need. Anybody outside with a question? All right, if there are no questions, everyone, please put your hands together for Mikael.
Thank you.